going to continue to explore the hidden symmetry in the Navier-Stokes. So this is what we had started last week, which is simply the study of what we may call the hidden Navier-Stokes equation. And just to remind you of the general setting, so what we want to do is to, in a sense, parallel the derivation of hidden symmetry in Sabra to the Navier-Stokes case. And in particular, the objects that were key to make intermittency appear in terms of multiplicative structure were the multipliers. So in Sabra, it was something like that, either the ratio of the shells or some generalized ratio, like that. While A was a function that was some type of coarse graining of those ratios. And so we had started to argue that the analog of those things here in the Navier-Stokes are the so-called Kolmogorov multipliers. Which are simply defined as a ratio of increments at along some prescribed directions. So those type of Kolmogorov multipliers here, they are the in a sense some type of analog to those type of ratios. And what we were we argued, or what I tried to argue, is that, well, it's not so clear from observation that those multipliers are universal, but it's not so clear that they are not. And so if we want to make a statement about universality of ratio, it's better to think of generalized ratio than specify a form like that, and in order to go beyond pure observation. And this motivates the quest for defining generalized ratio in the Navier-Stokes that would be really the analogs of those objects. And if we want to do that, then we need to go with the full story and perform a dynamical rescaling of the Navier-Stokes equations. So which consists, in a sense, so if we have standard time, standard position, and standard velocity, we are going to transform that into a new time, new space, and a new velocity. And in order to do so, we will need two ingredients. And the two ingredients are, I will just call them by x0 and L. And I will just try to recall those definitions. So the fundamental, so this x0 here, it defines a Lagrangian trajectories such that dx star over dt is u of x star of t and t with initial position x0. So we are, so that's the first component. So we have time t at position 0. We pick a position, and this selects a trajectory. So that at time t, here, so that's time, we are at position x star of t. So that's the definition of, yes, Bruno?
Would that work to make the same definition as this algebra to the Kolmogorov multipliers for the hidden level subs? Like you simply choose a shell and the next one or the previous to use.
Okay, we will discuss on today. We will specifically address on why that's a clever choice, which is part of the game. And then out of those objects, we are going to define some generalized, a new velocity field. So how it is constructed. So the first thing is to define some ratio. So let's we'll call that delta L of u of x star x t. It will be the difference of basically this object, but expressed in a with a certain size L, x star plus Lx minus u of x star. Okay, so that's we define this as just the increments along the Lagrangian trajectories, which are prescribed by a scale L. Okay, so that's L. And from that, we can construct several things. So first, we construct a new velocity field, which is u, which is nothing but this ratio suitably renormalized. And this normalization is taken to be a type of average around this ball here. For example, A, so AL is prescribed a functional called capital A applied to delta L of u of x star t, where A for all well, for today we can think of A as simply, for example, the average of a field along a sphere of radius 1, for example. We had seen that it was we could think of A as being more general than that. It has to just be a positive linear operator with homogeneity 1, but you can think of it today as just this simple averaging operator. And from that, so we have this object, which is defined, so that indeed it depends on x star, so this is the function of t and x0, and then the new time will be defined as d tau is dt over tau L, with tau L is nothing but L over AL. So this new velocity field here, it's a velocity field which depends on x, tau, and of course the two parameters here is to say x0 and L. And so the general idea is that here we are rescaling the velocity field both in space with this function. So in particular, some observations we can check that, for example, A of U is 1 for all time. And then this time here, this time tau, which is the integral between 0 and, say, t of dt prime divided by L times AL. This time is a time which is sensitive to the fluctuations of the underlying velocity field, which is sensitive to the fluctuations of this average felt here. And so when you have a strong bump, some strong intermittency, this goes fast, and so we are expanding time. And when there is a flat environment, this stops. AL is close to 0, so okay, it just flows, doesn't flow. So the time is stopped. So in some way, this time tau is a new time tau, which in a sense can be interpreted as a proper time. It's really some time which is felt by this particle through the lenses of this averaging. And so that was the construction which transformed an initial velocity field that solved the Navier-Stokes, for example, to this new rescale variable. So the observation was to say that in a sense, the property, if Txu solves MS, the Navier-Stokes, then the new variables, they will solve the hidden Navier-Stokes equation. Or the hidden Navier-Stokes are prescribed by the following formula: dt d tau of u is equal to some operator which applies to the right-hand side of the original Navier-Stokes equation. So that's the hidden Navier-Stokes equation, where all the derivatives here are taken with respect to capital X, where in fact you also have another equation which is the incompressibility, also with respect to X here. Okay, and well, the definition of all the quantity which appear here pretty much follow the definition of U here as differences, but suitably normalized in space. So, for example, capital P is delta star of L of P of X star X T divided by AL square. FL is L over AL square times delta L of the forcing or the forcing increments, and the nu L is the usual rescale velocity, rescale viscosity. So that was pretty much the construction. And so today we want to explore the consequence of this construction on the symmetries and on the symmetries of the original equation. Are there questions at this point, or it's pretty clear? So this is where we start. That we are going to talk about hidden symmetries per se. Yes.
Here your equations are, you're fixing the scale L, right?
Yeah. So L.
Of the M.
Yeah, it's a good remark. So L is like the M. So L is exactly like M in Sabra, but X0 has no counterpart.
Yes.
So that's yeah, we need so X0 is vector, so we need 4 parameters to make this transform. While in the Sabra case or sham model case, we only needed 1. So that's the main difference between the two cases. Okay. So hidden symmetries. So as in the Sabra case, we are mostly interested in looking at the properties of these equations for L, which is here prescribed, in the so-called inertial range. So remember that the inertial range is where we have drawn this graph now 100 times. So this is where we expect the scaling of the structure function. And this is delimited on the right-hand side by the forcing. And on the left-hand side by some viscous effects, called that eta. And well, below eta, we don't have anything. Okay. So we are interested in looking at the range of scale between eta and L, and that's precisely the inertial range. Where eta is following the definition that we gave the fourth course, the classical Kolmogorov scale. Okay, and so the property is that, or it's a hypothesis so for L in the inertial range, the Navier-Stokes equation, the hidden Navier-Stokes equation, which are prescribed by those equations here, transforms into the hidden Euler equation. Which are nothing but those equations, except that the influence of the forcing terms will be just neglected. And those are the hidden Euler equations. Okay. Now I realize that I have two things. So I forgot to remind what was this operator lambda. So this operator lambda was something which was not super complicated. It looks like a projection operator. So lambda applied to any vector field is V minus the differential of the functional applies to minus U to U and V. That was a general formulation. So for example, for A, which is prescribed by this formula here, then this guy is simply V minus U times U dot V average on x equal 1. So it's you have a vector, and a number. Okay. So that was the general definition that we gave the other day, and that's just the specific case where we assume that we have the norm average on a sphere of circle of radius 1. Okay. So now we go back to the story. So this is a classical hypothesis. So this is obtained just by assuming exactly this that this relation holds, and that f is of order 1. And so I just can just refer you to I think the second course, where we had done the same type of trick in order to eradicate the influence of the forcing term on the dynamics and precisely define the inertial range. So the inertial range is a range of scale where, at least at a heuristic level, you may say that this, which is prescribed by a term which is of order 1, will be dominated by that, and if L is very small, very large compared to eta, then this will be negligible, and similarly for this object. So the idea is that we are going to study the property of those equations which are prescribing the dynamics in this range. Okay. So what is the observation that we want to make for this equation? There are two observations that we want to make. So I remind you that the first observations, we make three observations. First observation is that U is a priori a function of x, tau, and as you wrote over there, x0 and L. First observation. Second observation is that L is nowhere appearing here. nowhere here I have an information about L, because those are functions which are P is related to U via this formulation, and in lambda it's this expression that we wrote here is something which is totally free from the specification of L. So in a sense, those equations have a meaning even if we don't know L.
But tau depends on L.
Yeah, but you see tau is here is prescribed here, so I can just define it as a time. And if I change L, so if I change L to L prime, then the new equation will be d prime of U prime is equal to lambda times minus, so this lambda which depends on U here, lambda of U prime minus U prime minus gravity prime. In that sense, change L, you get the same equation. It's a cool thing.
Why does it make sense?
Well, we are going to try to understand what it means, like 5 minutes.
The ball goes to zero, you're saying the averaging of the ball, but this is why does it make sense?
Yeah, so I will draw a cartoon. It will not be a game, it will be a cartoon. I think you will like it. And so let's just do real quick with the third observation, is that the hidden Euler, they do not depend on x0. Let's put a second. Okay? So in a sense, I can change x0 to x tilde of 0. And the equation will be unchanged in the same way that I can replace all the primes here by some tildes. Those two properties are the two fundamental observations that we need to make, and are the only observations that we need to make. And those symmetries, which appear at the level of the hidden Euler equations, is what we call the hidden symmetries. So this first property is something that we called the hidden scale invariance. And this one is a property that we are going to call the hidden translation invariance. So here they are being explicited as a function of L prime, and so the interesting thing is that those two relations can be interpreted as transformation on the field U and on the time tau. So let's write it so that you will have a feeling on what's happening here. Yeah, exactly. So they.
There's dependence on L, right?
Yeah, exactly. So there is dependence on L, which is. So it is in this sense that they are hidden. So they are trivial in the new coordinate system, but they are. We don't know where. They are hiding in the old coordinate system. So that's the idea.
In the hidden Navier-Stokes, those symmetries are broken because of the dependence on L.
Yes, exactly. So in the hidden Navier-Stokes,
The first one or the second one? I don't know.
uh,
There's also no dependence on x0 on the hidden Navier-Stokes.
yeah. So I think you're right. So I think you're right. So this one is okay for. So hidden Navier-Stokes okay. It depends on the forcing. So for constant forcing, for example, for constant forcing, it will be trivially satisfied. okay sometimes. This one, no.
But there is no counterpart like on Navier-Stokes and Euler scaling invariance, because Euler has a scaling invariance, and Navier-Stokes as well. Navier-Stokes is a restriction of the
Yeah, so, well, okay, this, but we will see why it's not a counterpart. It's related, but it's different, yeah. And we'll see that those type of invariants, which appears at the level of the rescale system, are in a sense weaker than all the symmetries that we listed for the original equations, in particular the scale invariance of depending on lambda and h. So let's write the hidden scale invariance. So we are going to change L to L prime, and let's specify this change as L over lambda with lambda 0, lambda equal 2, say, for example. And I will write the transform first. So if you do this transform, then U, X, and tau, they transform as U prime, X, and tau prime. So X will be unchanged, okay? With, in essence, U prime of X and tau prime. That will be what? That will be something that we are going to call U lambda of X and tau divided by the functional f, so it's suitably normalized. And d tau prime is lambda a of u lambda d tau, where u lambda of x and tau is equal to u of x over lambda and tau. So I wrote that in a barbaric way, but let's try to prove that in two different, to see why this type of relation is true in two different fashion. So that's the hidden scale invariance, means that if I change L to L prime, this is the corresponding change in the rescale field, is that you are transforming u and tau in u prime and tau prime, which are the u prime and tau prime which appears here. And there is an explicit expression for u prime and tau prime as a function of the original u and the original tau. Okay? So this looks very mysterious, but in fact, we can understand what is true in two different ways. So the first way is, I would say, a brute force algebraic way. So brute force algebra. Yes, exactly. Yeah. So yeah, so let's try to prove it, and then to do a cartoon, and then we will understand what it means. So just some algebra to see that there is, in fact, we are only dealing with elementary manipulations of those objects. So for example, I will start with u prime of x and tau prime. It's delta of L prime of x star x t divided by a L prime. So far so good. That's the definition that we gave here. Then the trick is simply to multiply and divide by AL. And then this object here is something that we can recognize. So this thing is u of x star plus L prime x minus u of x star divided by AL. L prime is L over lambda. So that's L over lambda. Okay? And so here we recognize immediately, by definition, that this is exactly u at x over lambda and tau. Call this u lambda. By definition, I call that u lambda. That's the first thing. And so then we are left with AL over AL prime u lambda of x tau. And then if you want to know what this factor is about, the trick is just to apply the operator A on both sides of the equation. Okay? Because of the very definition of u prime, this is 1. And so we are left with, so this, because of A is homogeneous of degree 1, this one can get out. And so we are left with AL prime over AL is exactly A of u lambda tau. Yeah, so this means that I prescribe that L is transformed to L prime, which is L over lambda.
So the equation does not depend on L.
Yeah, the equation. So indeed, so there are two things. So here I'm describing what it does to make this change at the level of the definition. Okay, and then. The claim is that when you do this transform, and then that when you are in the initial range, or when you let L go to 0, then the hidden Euler, the hidden Navier-Stokes become the hidden Euler, which does not depend on which L you take. That's the claim.
So this is before going to
Yeah, exactly. So that's in a sense purely kinematic. In a sense, we don't need Euler here. Just to say that if we make this change of variable, it means that this is how the definition transform. Okay, how they evolve is a different story. So that was the first. So AL prime over AL is exactly this. So we get exactly the first equation. Okay. So this means that we get exactly. So we get exactly here the fact that, so we get that u prime of x prime to prime is u lambda of x divided by A of u lambda. First, and of course we need also to do the time change, but the time change it will be the same. So d tau prime by definition is dt over TL prime. Okay, TL prime, it's L prime times AL prime. And that's AL prime over AL times 1 over L prime times, AL dt over L times L. So I do the same trick. I multiply twice by AL and I multiply and divide by L. And here I have exactly d tau. Here I have exactly the object that I just computed here, A of U lambda, and L over L prime with L prime, which is L over lambda. This is exactly lambda. So, check.
It's still confusing to me because you're scaling in L, and that's the hidden scale invariance. But then when you take the limit, it does not depend on L. So what's the hidden?
Yeah, so we will, so those maybe if I can rephrase it, the confusing part is that indeed, a priori, for a given x0 and L, they will satisfy the hidden Navier-Stokes equation. And the hidden Navier-Stokes equation is not invariant with respect to the change, to the change of L because of the forcing and dissipation. So that's so what I'm saying here is simply what does this when you change L, okay, maybe it will become invariant in some limit, where the Euler equations are going to be the relevant equation. Okay? And so the question that we are asking is what does it mean at the level of the fields to make a transform where you change the L, which is the observational scale? That's what we are asking. And the answer is that if you have the fantasy of changing L, then you are transforming the rescaled variables in this fashion, which is non-trivial. It's in particular non-linear in U, and that's purely kinematic. So maybe I'll draw a cartoon, and I think you will see that it's this algebra is true, so it's totally elementary, but perhaps not very insightful.
When you work with the Euler equation, scale invariance, say here, it's not going to be there, right?
For now, yes. So yes.
It's going to be gone, right?
Yeah. So the fact that I state that the dynamics is invariant under the transformation L goes to L prime incites you to understand what is this transformation doing. So I have a transformation, and I want to understand what it means to perform this transformation. And so here, when I write this transformation here, the claim will be, okay, if I change the field U x tau to U prime x tau prime, then U prime to x tau prime will satisfy the Euler equation. Okay, but the definition of U prime and tau prime does not depend on them being on the equation being invariant with respect to L. That's so let's so this was the brute force proof, and now the cartoon proof. So we have our trajectories. We have the first, so let's put some yellow for the first. Okay, this is what you want L. This lives in time tau. And so in the reference frame of the trajectory, this is L, but in the reference frame of the particle, this is 0, and this is 1. Okay. So now we take lambda equal to. Let's put this. Let's take lambda equal to. So L prime, so this means that L prime is L over 2. Okay, so in this reference frame, I'm going to draw something like that. That will be L prime. So it has here, so let's put it this way. This has radius 1/2. And this evolves with respect to tau. Now, I'm doing the same thing, but I'm rescaling with respect to L prime. So this means I'm taking this guy here, and I expanding it, so that now this is L prime. Okay, so now this is 1. So this is the new 0. This is still the old 0, and this is 1. Okay, and now what I'm asking is what is the velocity field if I take a random position. So I put myself here. I want to know what is so that's x here. I want to know what is the velocity field at this position. Just read what's written here. The velocity field u prime at x here is just the old one at x over lambda. So the old one, so if I draw x here, so x is here in this new in this rescale coordinate, and lambda is 2, so I just need to divide by 2. Here I have a velocity field in this. This is u of x over lambda, or x over 2. And so this velocity field here is nothing but this one here. So this one relates to this one. It has the same direction, but it's rescaled by that's exactly u lambda of x over 2 sufficiently normalized by what's happening here. U. Oh, yeah.
No second.
Yes, thank you. Okay, and the only thing is that so that's for the graphical part. And the only thing is that maybe the time has not evolved in the same way. So this has to be taken with respect to a normalized time. So if you synchronize the clock to what's happening here and the clock that was happening here, then you can make a correspondence between the vector at that position and the vector at that position. And you see that in this cartoonesque way, it seems almost trivial. This is what you see, that in fact changing the reference frame, changing L to L prime, it's just really making a different choice of zooming and a different choice of observing your system. But it's true that this guy here, if I take a certain L prime, should be exactly related to the velocity field at a distance which is twice smaller if I were to take the L twice larger. That's the idea. And so in that sense, this set of transform here, which is written here, we can interpret that as a transform which is some type of kinematic consistency. It's a consistency condition. So the system is the same. The system remains the same no matter how you observe it. And how you observe it is by choosing L and A. That's the idea.
Why is the forcing term go to 0?
What?
Why is the forcing term disappear? Forcing term in the original equation.
Why does it disappear? Because so we are the forcing term. It has some scaling L over L squared, which, if you assume Kolmogorov, it's something which is L over epsilon 2/3, L 2/3, for example. No, sorry. No, it works. Sorry. Okay. And so if L is very smaller than 1, then this is that's the ID. So this is L 1/3. That's if you take L, which is sufficiently small, then this term here is just gone. Okay. So now let's just write down the second transformation. So that was the hidden scale invariance. Now let's write down the second transformation, which has the hidden translation. So the hidden translation is invariance with respect to a change of initial point. If you do that, then the same thing, the initial rescale velocity is going to transform as tau tilde x and u tilde. And so what will appear, so this one is a bit more complicated to state, but there will be also some functional of the old field that will appear. So in practice, u tilde of x and tau tilde, it's u of x plus a new center minus u of x star. So call that following. So call that delta u of x star and x divided by a to delta star of u. D tau tilde is a of delta star of u times d tau. And we just need to specify what is this guy. And so this x star, it's simply a Lagrangian particle obeying the equation dx star over d tau is equal to u of x star with, so let's put that initial position. So if we say that this is, for example, just a shift, so x tilde 0 is x0 plus L of x tilde 0. This will be x star at 0 is x tilde of 0. So make a short break and then we do a picture. So back in 5 minutes.
Maybe you want to say that you can forget about the first line and then just consider transformation per se. And this transformation doesn't change the hidden order equations.
Yes, so I will say after yes. So break. Now. picture, as promised. So we'll make the same type of picture as the one which is here. Let's try to improve on the drawing. How does this work? So we are making a change of initial point. So we have the trajectories, which starts at x0 in the regular time here. X time, x star. And so here we are making this change. Okay, so we are shifting. We are taking a new trajectory for starting at x tilde of 0. And so in the old unrescaled reference frame, the distance between the two initial points is what I call here L x tilde of 0. That's the distance between two initial points. And then, so in the reference frame where this is L, okay, this distance is simply x tilde of 0. Just divide by L, okay? And so this point here, so let's put it here, it follows another trajectories, which is what it is. So such that in this reference frame here, I have a velocity, call that u of x star. So this in the reference frame of this in the yellow reference frame, this is the position x star, and this and x star is simply in the old in the white reference frame, that's L x star. So laboratory, so that's the color code is that's the laboratory. Laboratory. That's the reference frame L x0, and that will be the reference frame L x tilde of 0. Okay. So in the reference frame, the yellow reference frame, this has position 0.
Sorry, which one is the white one?
White one is the old one.
Which is not shown.
Yeah, so basically in the old one, you take a Lagrangian trajectory and it flows in the regular time. In this reference frame, then this reference frame is centered at about the first trajectory. So that's L, and that's 1.
What is 1?
So in the yellow reference frame, this is 1. But this is L in the old, and so.
And the red?
And the red, so the red will be centered here. They have the same L, so this is again. So this is 1, and this is position 0. Okay. So in this reference frame, the velocity is vanishing. So what we want to say is that u, so that's x star, huh? And so what we want to know is that what is the velocity in the red reference frame? In the red reference frame. So I take something, say, to be simple, I want to know what is the velocity here. And then I just look at the old, which is the yellow one. Yellow one, up. It will be u at, so that's,
But if you draw a vector, you say it's 0 at like a x star, or
yeah,
you draw an arrow.
yeah, you're right. So that's x. So that's vector x. And the question is, what is the velocity here? It will also be an arrow.
But what is 0? X star is
0, so the red 0 is the yellow x star.
all right. So yellow is
Yeah. And so I want, so the velocity at this position x here will be the velocity at x at x star plus x. So it will be, so that's u of x plus x star minus the velocity at u of x star. Velocity at the yellow velocity at x star is this one. Okay, so I take minus this thing. And I come up with the velocity of u tilde at position x. Yes, sorry. So say that this has a velocity which will be like that. We'll draw it like that. Up. So that's u of x plus x star. And that was not, that's x plus x star. So this velocity here, if I subtract this velocity, this will give me the new velocity u tilde of x. So in a sense, it's also like it's the same as the first transformation. It's just a consistency condition. So I want to be really describing the same object, but okay, with different viewpoints. So of course, the deal is that now because we have a new velocity everywhere, also the time is going to change according to this new velocity. Yeah, we have tau tilde, which will be something which will depend on the integration here. So this is what it means. It means that I can change, this change of reference frame in the old variables becomes a change of reference frame, which is a bit mind twisting in the new rescaled velocity field, but this is also what you may call a consistency condition, like also the consistency condition. So that's the idea. And so the claim so what we may really call now as the hidden symmetry. It's another change x tau u gives x to prime u prime, and x tau u gives x to tilde u tilde. The hidden Euler equation is unchanged. Or in other words, out is exactly out of an old solution, I can construct a new solution. And that's what we call, so hidden symmetry are symmetries of new equations. So this one is the is the hidden scale invariance. Hidden scale invariance. And this one is the hidden translation. Hidden symmetry means symmetry of the new equation under those change of variables. And this one, in the old framework, that's L goes L over lambda, and this one is x0 goes x0 plus L x tilde 0. That's it. So now what we do with the symmetry. So we have the symmetries, so let's talk about fusing symmetries. Why is it interesting? Why is it different than the old symmetries? Fusing symmetries. Let's start again here. So we're going to do some. Let's start with. We're going to do the same type of diagram that we did for Sabra. So suppose that we start from the Navier-Stokes equation, or from the. Yeah, so start from. Navier-Stokes, in fact, it doesn't really matter. Where you have U, X, and T. That's your. So from that, you may go to hidden Navier-Stokes. That will be prescribed by capital U, X, and tau. And the only thing that you need to do is to specify x0 and L. Once you have that, we can transform this object here by just going L goes L over lambda, and x0 stays the same. And then you recover the hidden. So let's put Euler. The hidden Euler with the U prime X so prime. That's what we just did. Is that if you transform your original equation by doing your dynamical rescaling, then after it doesn't matter really how you did it, because you can always transform the way you observe your original system, and you will get the same system, but with different definitions of the variable. And this you can do from here. But then you can do it the other way. So if you do that, so you start here with something, you observe it at a certain scale. That's what we observe. Poof. And then up by doing this transform, you just magnify. You just get a big circle. Just magnify it. Now you can do it the other way. You can also perform a rescaling, like a usual space-time rescaling. Space-time rescaling, which depends on lambda and h. Lambda greater than 0, h not equal to 0, such that what? Yeah, but if h equals 0, it's a bit weird, no? Anything formally, but yeah. And then you get again the Euler, who is now lambda h u lambda x lambda 1 minus h t. Now you have this Euler. What you can do is you can try to apply this transformation. So if you do it this way, so if you take the same L and multiply x0 by lambda, recover the transform that we did on the other side. So exercise, so check. So check this side, actually. And so here we have the, so what it means is that if you, well, it works in a sense, if you don't care about the equation, it works because it's purely kinematic. But if you want to say that the transform leave an equation invariant, then it works only for Euler. So if you want to take those transform here as symmetry of the dynamics, then it works only for Euler. But if you want to take them as just kinematic constraints, it doesn't matter. And so here you have, so what it means is that you observe. So if you zoom first time and then if you zoom a second time, it's the same thing as if first you magnify and then you zoom.
But the hidden Euler does not depend on L. So how can you, why are you doing the transformation in L if it does not depend on L?
Well, you see that, yeah, because so here what it means is that when I say that, it means this transform. Or in other words, so if you could remove Euler if you want. So if I do those transform like for an arbitrary field, then this diagram commutes. Okay. Now if I take Euler, if I impose this to be a solution to Euler, then this will be a solution to hidden Euler. This will be a solution to hidden Euler, and this will also be a solution to regular Euler. That's the way you can think about it.
I guess my question would be the L to L so many lambda is like in the right part is sort of trivial because there's no dependence on L.
There is a dependence on L here for the definition. You define it with a L because the L is here, but if you want, yes, yes, you may say, yeah, this is indeed a trivial observation when you are looking at the hidden equation. The hidden equation does not depend on your scale, so it does not depend on your scale. That's indeed it is in a sense trivial, but if you were to see it from the point of view of those transform and try to check it directly, maybe it would be less trivial. And so here the observation is as in Sabra. So here you have something which depends on H, and here we have something with that. Well, but in fact, if you go this way, in fact you see that this field can be obtained without any H dependence. So you have also this kind of fusing of the space-time rescaling. The sense that the hidden scaling symmetry is blind to H. So it's blind to the underlying roughness, if you want. That's cool. It's cool. So this is exactly. So we had the same. We had exactly the same diagram for Sabra, with the only difference that there was no x0, so up, and L was M. So CF Sabra with no x0 and M instead of L.
Sabra is also blind to H.
Exactly. So that's exactly what I'm telling. So in Sabra, the hidden scaling symmetry well, it's not the invariance with respect to L, but invariance with respect to M, so the reference shell. So the reference shell is what we call the observational scale here. And we have the same magic which is appearing, is that the rescale equation do not depend on H. They do not fill it. And in that sense, okay, so for more, wait until Friday. But the property of those symmetry transform is that, in a sense, it projects a symmetry group, which is here, which is 2 parameters, into a symmetry group, which is only 1 parameter. That's cool. So we can do the same diagram. So that you say, okay, we may say, yeah, but this we knew because we know Sabra. That's the same. Now we have another one. And the other one is so we keep in mind those definition. So we can do the same thing. You start with Euler. So the first line is the same. And then you do x0 L, and then you get hidden Euler in terms of U, X, and tau. So if you do that, you can. So what we did is that we changed the initial point, but keeping the observational scale intact. And then when you do this transformation, you get again the hidden Euler, but with a new field U tilde X to tilde. And the same thing, you can do it, same thing, but going under the side. So what you are going to do is that you may, of course, you may say, okay, you may just add a translation here. So, and that will keep U unchanged, T, okay? So here you put space translation. The interesting thing is that you can add another layer. You can also include a Galilean transform. Yeah, so it's the same. The Galilean transform. Which depends on U0, where you are going to add a U0T here and a U0 here. And if you do that, and then you reapply this transform with the same x0 here, in L, you end up with the same field. Check it, it's fun. Check this path. And so here we have again a type of fusing which is appearing. So here we have a 3-parameter group which depends only on x0 in R3. So this is in R3. And this is R3. Here you have L x tilde of 0, which is in R3. So you have R6 to R3. You have a fusing as well. Fusing. So the same way that the hidden scaling, here the hidden translation is blind to Galilean transform. So we have removed Gaussian transform in this framework. So, in a sense, the hidden Euler are less sophisticated than the Euler because their symmetry group is larger. So that's the two fusing of symmetry which are important. So now we are going to explore the idea of statistical restoring. So again, so this one has no counterpart in Sabra. Again, this one is the same as Sabra, but this one has no counterpart in Sabra. No counterpart in Sabra. So that's what the fusing of symmetries. So now, what we are going to discuss is the statistical restoring of symmetry. Statistical restoring of hidden symmetry for Navier-Stokes. It's not bound to lambda, exactly. So out of so you can still rescale the space, but you don't have to rescale the velocity. And yeah, the reason is also, well, that's why I mean we need to do both the space-time rescaling because okay, you may say we are dividing u by u, so that's why the h is bound, but there is also this t which appears, so that's why there is kind of intricate magic which appears in those equations. So for hidden Navier-Stokes, clearly the hidden symmetries are broken by forcing participation. So in the same way that in the audio Navier-Stokes we could appeal to some type of restoring of symmetries at the level of the measure, this is what we are going to do now. So still, okay. So we want to the hidden symmetries may be restored in a statistical sense. So let's take, for example, so I take something that I will call an observable phi of x0 and tau. Okay, that will be just an observable of my field U. Okay, so that's U is the rescale variable, and so for this I want to be able to take an average. Why? Y is 0. X. If I average, it will be a function of x0. Yes. Phi of x tau is a function of all of you. Yes. Okay. So it's really so. Take O for example. Anything like O can be U square average of on X, for example. Something which is just a function of the rescaled field. And observable, which can be anything. Average in X, for example.
But then it's just tau. It's just phi of tau.
Yeah, it's a phi of tau, if you want. Let's put it this way. Phi of tau. But a priori, it depends also on x0 and L.
Yeah, x0 is
Yeah, but you're right. You're right. Yeah. X0 and L. This way. So I want to be able to define a long-time average. Okay. Poof. I'm making an average with respect to tau, and so I have an average with respect to tau. And I will also average with respect to x0.
Taking a limit here.
For now, no. And so I will call. That's what. So I will call the hidden turbulent measure, if you want. It will be defined by the limit of phi. So the limit when tau goes to infinity of the limit of nu goes to 0 of the limit of L goes to 0 of phi defined on x0 tau, which a priori depends on nu and L.
What is the average over?
So I have my field. So the field.
there is no tau goes to infinity because you average over tau.
Yeah. So okay. So
Tau goes to infinity.
yeah. Well, it depends on. Yeah. Okay. If I call tau, which is just 1 over tau equal to 1 tau. That's just a matter of definition. Okay, and so in this triple limit, I want to call phi star hidden.
Assuming that exists for all phi, that's what gives you.
Yeah, exactly. And so the statistical restoring of symmetry means the hypothesis that this limit exists. So yes, so here you have there's a subtlety that we are averaging also in space here. Average with respect to x0.
But the measure is what's in the space. The three-dimensional space.
Yes, yeah. It can be.
Measure on
It's a measure on the field U.
on the space of fields.
I have a space of field which is exactly this. So if I want to define. So I want to define a measure for the hidden Navier-Stokes in the limit of nu L goes to 0. The hidden Navier-Stokes is just an equation that I may consider for what it is. And so the way I do it, I will just consider any functional of U, which U is a priori a function which depends on x, tau, x0, and L, and nu. That's
Any observable is a function of thing, and the measure is
And what does it give you for the space?
so that's phase space.
it will, for example, it will tell you what's the PDF of U. If you take, for example, take R of U, it's I don't know 1 of U in circle UI in the U. That gives you the PDF of your field.
You
Of
at
your-
certain point.
Yes, exactly. UI, we'll have x, how do I specify it? X0 in dx. That will give you du, if you want. That will give you something that you may want to call P star of H of du, for example. And so, yes, so that's the thing. So what we are going to call a statistical restoring, so statistical restoring of hidden symmetry, and that's a hypothesis. C star H exists. That's a hypothesis. Like I want to say that, okay, if I take those limits in those way, I get something which is not zero and which is not infinite, and that's well defined in a probabilistic sense. Yes.
Well, why are you taking the limit L going to 0? Because like I was wondering that you would like to stay on.
It's a matter of style here. You could try to define just this limit, and then say that so if you were to take this limit, then you may define this as the turbulent measure for the associated to the hidden Navier-Stokes, and then say, okay, the property of statistical restoring is that this limit, the limit of the turbulent measure, which is dependent on L, is well defined, or we can just take the limit from scratch. It's a matter of just definition, convention. This way.
L is much more than 1.
Yeah, nu over 0, L goes to 0. That's
And
it.
it shouldn't depend on that.
Exactly. So in practice, what does it mean? That in practice, we expect that. So in practice, that this H, which a priori depends on nu and L, is independent from L in the inertial range, L1 eta. That's always the same trick. The same. Okay, we assume that we have certain limit that exists. In the real world, what does it mean? Well, we have finite viscosity, then it means that there is a range of scale for which I think, or we claim that the measure that we obtain for finite value of the viscosity and the scale do not depend on the scale. So the limit is well defined, which is the same type of trick that we've been using, and the same type of trick that we use to, for example, identify scaling exponents as the Perron-Frobenius eigenvalues in a certain limit, which we can measure in the inertial range. So very.
With respect to U, there should be some
No, here it's really like we are really imposing this type of condition. It's that
VHUL
yes.
U. Scaling. VHUL. Does not depend on L, but with respect to U, there's some scaling problem.
Yeah, so and this is this condition has to be satisfied.
No, with respect to the other variable. The V.
I don't understand the question.
That one is not. Which one? It depends on mu and L.
Yeah, but
And it says it's
in
independent of
asymptotics, when mu goes to 0. Asymptotics, mu goes to 0, means it does not depend on mu. If there is just the assumption that there is a limit at mu goes to 0, means that for small mu it stops.
Yes.
Is the hidden measure Gaussian in any sense?
No, I can show you. It's not. Really. Well, that's a very good point. It's so we say, okay. So here we have a measure which is defined along the Lagrange trajectory. So is it useful at all? You may ask. So the claim here is that so claim. Or,
So you have to go back to the, it's still a hidden measure, right? You have to go back.
yeah, exactly. So property under the assumption of ergodicity plus space homogeneity, then phi star of HS, so the limit of the hidden Navier-Stokes is connects to the limit the real turbulent measure. So that's the turbulent measure of old Navier-Stokes. Okay, and so the only thing is that so here the way to do it is that you see that's natural. So if u remember that u is just a function of delta small u divided by al. Okay, and al is just a functional of delta L of u. Okay? So this you may as well think as an observable that you may call phi in x t. Okay? With the change of variable when you go from x0 tau to x equal x of x0 t, x t x0 and t. So you can transform an observable which is expressed in the new time and which depends on x0, which is essentially a Lagrangian observable, into an Eulerian observable, which depends on the space and on the regular time. Okay, and the price to pay to do that is that you are going to be indeed this average here, and we pick up. So that's xt, and here you will pick up a Jacobian factor. J is a Jacobian associated to transform x0 tau goes to x equal x of t x0 and t. And so we can show that g of xt. So this Jacobian will be finite if only if we can make this this transform is well defined. So this will be exactly AL of xt divided by AL of xt star under the assumption of incompressibility. So, in a sense, if you want to connect your hidden measure to your new measure, you need to be able to have a factor which does not vanish here, and this is given to you by the assumption of incompressibility. If you didn't have this type of assumption, for example, if you were to think to apply this type of rescaling to burgers, you could do everything. You could even define you could even make this assumption of statistical restoring of hidden symmetry, but then you could not go back because all the trajectories, for example, would be trapped in a shock, and so there would be no way to probe the entire space given basically a collection of random trajectory that evolve in a long time. So you would just probe the most singular structure in your flow that will provide you also with some type of that will be the mechanism for the fusing of symmetries, but that will not allow you to recover the whole measure.
Here you're assuming that both exist, right?
Yeah, so what I'm assuming is that if this exists, and if this exists, then I have this relation.
But then can't you, if you
Maybe we can do something a bit stronger, saying that if this exists, then this exists, which is most presumably true, because in fact, the only thing that you do is you make here almost a trivial change of variable here, like a Lagrangian change of variable. So this, okay, but then you need to assume that this is well defined in a sense.
in general, maybe it's not unique, right? Maybe it's got a finite number of measures. That's the general situation, right?
Yes, I mean, yes, yes. Yeah, so.
The observation suggests that probably it's unique, but nobody knows.
We don't know. Like this is what we would like to define as the most natural measure. That's what we have in mind, but I don't know any proof. I don't know if there exists any. So that's more like that's more like a scenario, if you want.
Existence is not. You can prove this or not? This one?
No, I cannot prove.
It's just observation.
Observation.
Even for the Sabra model, you can't.
You can prove it for this solvable model.
Yeah.
For solvable shell model, you do this completely, the whole problem. But for Sabra, it's numerical, but very clearly true
Yeah.
on numerical level, and for Navier-Stokes, it's presumably in agreement of observations.
Yeah. So here I want to do some conclusions, but rather I think that some more general conclusions will be given by Alexei. So yeah, perhaps I will just show you. So that's basically this relation is a way to map a measure on which you assume that you have some independence to something that you can actually measure in a simulation. And this is simply a measure ponderated by a Lagrangian factor, well, by a factor which is non-constant in space, and which reflects the fact that we have been mixing the time in a kind of strange manner in our dynamical rescaling. And so if you do these type of things, and if you try to look at the statistics of functional of ratios in the Navier-Stokes, this is what you observe. So where is the?
In practice, is it easier to find this one or the other one?
What do you mean?
The hidden one or the real one? Like, is there an advantage to like try to find this one?
So I would say this: like, if you're talking from you're talking from a theoretical viewpoint or from a observational viewpoint. Numerical viewpoint. This one is so this one is a nightmare because it means that you need to track some Lagrangian trajectories. So it means that you need to have information on the field and on the transports, which is generated by the field. So that's a nightmare. But if, on the other hand, the other one, where you just take a snapshot of the field and then you measure, you identify the turbulent measure to, for example, average on X through the hypothesis of homogeneity, then this is something you can measure easily. Like so the hidden turbulent measure is cool for symmetry, but so practical for symmetries because it's more simple. But to measure it, it's complicated because it is built on a quasi-Lagrangian framework, and quasi-Lagrangian means Lagrangian, and Lagrangian is complicated. That's a mantra in turbulence. Lagrangian is complicated.
But it's not simple. So now
Yeah.
we can have a relation between those two. So originally we use all simple see relation between.
So okay, so if we take like a classical, so okay, that's a typical simulations where if you observe PDF of increments in a normal way, you see like a standard type of intermittency in the way that we mentioned previously, and that's typically the type of PDF that you get if you measure observable of the rescale field, okay, which we may prescribe. For example, if I look only at the parallel component of the rescale field, and I measure the PDF according to the formula that we have, this is what we observe. So typically, for L over eta here indicates the ratio between the scale, the observational scale, and the small scale here, and you see that there is a reasonable collapse of curves that we see, and compared to the Cauchy PDF that we had previously, one can observe that we still have algebraic tails, but they are less. They are steeper. So in a sense, we can have a better faith in the convergence of those curves because those PDF have a better evaluation than the I would say the usual Kolmogorov multipliers. So this type of collapse suggests that this statistical restoring of hidden symmetry is a plausible scenario that needs to be refined, needs to be better understood in both practical way and general way. For the general way, I think Alexei will tell more on Friday. I think we have to leave the room, but I can show you after.